Hello everyone, welcome back in this next video. Now let's solve furthermore some linear algebra question which are asked in the GATE examination in the previous year. So let's start this video with first question. Question 1 says M is 2 cross 2 matrix with eigenvalues 4 and 9. The eigenvalues of M square are what? Okay, we have given the eigenvalue of this matrix M and they are asking about the eigenvalue of matrix M square. So now here simply we have to use the one of the property of eigenvalues. Now let's call this value here this 4 and 9 as lambda 1 and lambda 2. Now let lambda 1 and lambda 2 are eigenvalues of matrix M. Then from the property I can say the square of this value it means lambda 1 square and lambda 2 square are nothing but the simply just eigenvalues of matrix M square. Now here simply property says whatever power this matrix will have, it is its eigenvalue is just simply the same power of the initial eigenvalue of this matrix M here. Now simply to find the eigenvalue of this M square matrix, we have to square those two numbers here 4 and 9. So 9. So now the square of 4 is 16 and the square of 9 is 81. So I can say option B contain the correct set of eigenvalue which are corresponding to this M square matrix. Now let's solve question 2. Question 2 says the rank of matrix M. They are asking about this the rank of this matrix M here. Here this matrix M has 3 cross 3 dimension. So now one conventional method is that we simply have to reduce this matrix M into echelon form. From the echelon form we can say the number of non-zero rows it is equal to the rank of this matrix M. But here if you look at the entry in this matrix M, so you can see only the two numbers are there 0 and 1. So now finding the determinant of this M here it is easier and the determinant is directly related to the rank of any matrix. So now I can say if I am finding the determinant of this matrix M and if I got the determinant at non-zero, then I can say the matrix M has full rank, and if the determinant of this matrix M is 0, then I can say matrix M is rank deficient. The rank of M is here matrix M is rank deficient. So now here the matrix M has a 3 cross 3 order, so I can say the full rank mean here in this first statement matrix has rank as 3, and now here in the second statement the matrix is rank deficient. It means the rank of matrix M here must be less than 3. So now let's find the determinant of this 3 cross 3 matrix M. So I can put it here. So simply 0 1 1 1 0 1 1 1 0. So now let's find the determinant. So the first element corresponding to the minor of this 0 will be 0 and minus 1 times the minors of these 4 entries. So I can say minus 1 plus 1 times 1. So the determinant is 2 for this matrix M. So I can say the determinant of this matrix M is non-zero. It means all the rows or all the columns of this matrix M are linearly independent. If this is going to hold, then and then we are getting the determinant as non-zero. So now I can say the rank of this matrix M is full, or in the another word the rank here is 3, because remember the basic concept of rank of any matrix must be less than or equal to minimum of its dimension. Here the dimension are 3 cross 3. So now I can say the rank of matrix M here must be less than or equal to 3. So now here the matrix M has full rank. It means it has maximum rank it could have. So here the maximum rank that matrix M can achieve is 3. So I can say the rank of matrix is 3. Now let's solve question 3. Question 3 says the number of distinct eigenvalues of the matrix A. Okay, we have given a matrix A which has dimension of 4 cross 4, and they are asking about the number of distinct eigenvalues of matrix A. So now here look at this matrix A. We are calling this type of matrix with some particular name. Here if you look the entries in this matrix A, then you discover something like triangle like this. All the entries in the matrix A are in the triangular form. So now this type of matrix we are calling a triangular. In particularly, this matrix A is upper triangular because if you look the entries above above this diagonal, all the entries are non-zero. So we can say this matrix is upper triangular matrix. If opposite is true, it means if the all the entries below the diagonals are non-zero, then we are calling a lower triangular matrix. But here this matrix A is upper triangular matrix. So I can write here A is upper triangular matrix. So now any triangular matrix has one property related to its eigenvalue. For any triangular matrix, its eigenvalues are nothing but just simply this diagonal entries. So now here in this case, the diagonal entries has value as 2. So it means first eigenvalue of this 4 cross 4 matrix A is 2. So I can say lambda 1 is 2. And the second eigenvalue is come from this second element. So I can say lambda 2 is 1. And the third eigenvalue will be this. So I can say lambda 3 here is nothing but 3. And the last eigenvalue here is again 2. So I can say lambda 4 is 2. So now here matrix A is 4 cross 4. So it must have 4 eigenvalues. But now here look at the eigenvalues. Here this 2 is repeating here again. So I can say this 2 is repeating twice. So now they are asking about the number of distinct eigenvalues. So it has only 3 eigenvalues if I am counting in the distinct way. So 1, 2 and 3, because here these two eigenvalues lambda 1 and lambda 4 are equal. So I can say this matrix A has 3 distinct eigenvalues, and which are 1, 2 and 3. So here they are asking about the number here. Number of its mean how many eigenvalues are there which are distinct. So I can say the 3 eigenvalues are there which are distinct to each other. Okay, now let's solve next question. Question 4 says a matrix P is decomposed into its symmetric part S and q-symmetric part V. If we have given a matrix S and also a matrix V, and they are asking about the initial matrix P, which is decomposed into its symmetric part and q-symmetric part. So here this matrix S is symmetric. So let's put it here. This matrix S is symmetric matrix. Symmetric matrix. And here this matrix V is q-symmetric matrix. Now look at the entries in this S. The definition of symmetric matrix is nothing but if I am taking the transpose of any matrix, and in the output after taking the transpose I am getting the same matrix which is the initial one. So I can say the matrix is symmetric. Is if this condition is going to hold, then the matrix A is symmetric. And for the q symmetrics, if I am taking the transpose of any matrix, and if I am getting the negative of initial matrix here in this case A, then I can say this matrix A here according to this condition is q symmetric. So now the symmetric matrix is one which has all the entries along this diagonal are mirror image. So now look at the entries here. So you can see if this diagonal is nothing but mirror, then this 4 is reflected here, this with this 4, this 2 is reflected here, this 2, this 7 by 2 is also reflected here. So now I can say this S is symmetric as given in the question. So now in the skew symmetric matrix, the values opposite to the diagonal are negative. So now let's again look at this. Here we have negative 2, so here we have plus 2. Here we have plus 3, so here we have negative 3. Here we have plus 7 by 2, so here we have negative 7 by 2. So yes, this matrix V is also satisfying the properties of Q symmetric matrix. So I can say this S and V are symmetric and Q symmetric respectively as given in the question. So now from the basic concept of this matrix, I can say any matrix, let's call it P here, it's decomposed into its symmetric parts and Q symmetric part. Here the symmetric part is nothing but the matrix P plus P transpose. If I am adding any matrix with its transpose and I divide this matrix with 2, then this matrix is nothing but symmetric matrix. And for the Q symmetric matrix, if I subtract the transpose from this initial P matrix and again divide this matrix with 2, then this second term will represent Q symmetric matrix. So let here write this matrix is nothing but symmetrics, and here this second matrix is nothing but Q symmetric. Now here this condition is going to hold for any general matrix P here. P may be any matrix. So now here I can replace this symmetric matrix here with matrix S, because here in the question it is given that S is symmetric part, and here this second part will be replaced with matrix V because it is Q symmetric matrix. So now our initial matrix P, it is nothing but just simply the sum of those two matrices S and V. So now simply I can write here. So let's make our resultant matrix P here. So simply we have to add those two matrices S and V. So now let's start with this first element. So minus 4 will add in this 0. So I can say the first entry will be negative 4. Now the second entry here is 4, and here we have minus 2. So I can say the second entry here in this matrix P is 2. Now the third entry here 2 plus 3. So I can say 5. And now here this 4 with this 2, so I can say 6, and this 3 with this 0, so again 0 here, and here this 7 by 2 plus this 7 by 2, so I can simply say 7 here, and now here this 2 with this minus 3, so I can say minus 1, here this plus 7 by 2 minus 7 by 2, so again 0 here, and the last entry will be here this 2 plus 0, so I can say 2 here. So now look at the option. You can see option A is the correct matrix. Sorry, here this 3 as 0, so here this entry is 3 not 0. Sorry, here because this 3 is going to add in this 0, so 3 plus 0 is again 3. So the option A is nothing but our correct matrix P. Now these all are the wrong matrices for this matrix P. Now let's solve question 5. A 4 cross 4 matrix P is given below. The eigenvalues of P are okay. Here we have matrix P again, which is a 4 cross 4 matrix, and they are asking about the eigenvalues of this matrix P. Now here this matrix P is fourth order, so it means it has 4 eigenvalues. Let's call it lambda 1, lambda 2, lambda 3, and lambda 4. So now the one conventional method is that we have to find the characteristic equation with this determinant P minus lambda I, and we equate this determinant equal to 0, and from this determinant we are getting our characteristic equation, and here our characteristic equation is in the polynomial with fourth degree because this matrix P is 4 cross 4. So now from this characteristic equation we can solve for this 4 roots of this lambda here, and we are get the values of eigenvalues here in this question. But now here in this MCQ type of question, simply we have to use the properties of eigenvalues which relate the eigenvalue with its matrix determinant and matrix trace. So now simply we have to use the two of the property of the eigenvalues, and first property says if I am adding all the eigenvalues, here the eigenvalues are lambda 1, lambda 2, lambda 3 and lambda 4. So let's write here, if I am adding those four number here, so it is exactly same as the trace of any matrix. Here the matrix is P. So I can write the addition of those four number is trace of matrix, and the second property says the multiplication of all the eigenvalues. Here we have four eigenvalues. So I can say the multiplication of those four number is nothing but the determinant of matrix P here. So now first of all, let's find the trace of this matrix P. And here the trace is nothing but just simply the sum of all its diagonal elements. Here the diagonal elements are 0, 3, 6, 6. So let's sum those four numbers. So here the sum of those four number is 15. So now the trace of this matrix P is 15. Now let's also find the determinant of P, because we also need the determinant. So now here, let's put it here. Here this P matrix is 4 cross 4. So first of all we have to decompose this matrix into the minors, and then we can find the determinant of third order matrix easily. So now here if you look the entries in this matrix B, it is easier to decompose this matrix with respect to first column, because it has only one non-zero entries here, this negative 2, and all the remaining 3 entries are 0. So in the determinant of this matrix P, we are getting only these minors of this negative 2. So now let's find the determinant. So now remember the sign factor. Here this element will be plus, this will be negative, again this plus, this negative. So I can say the minors of this negative 2 is nothing but negative times negative 2. This factor is multiplying with this third order minor. So now just simply delete this row and this column, because this negative 2 is contained in this second row and first column. So now after that I am getting this 3 cross 3 matrix. So now let's find the determinant of this 3 cross 3 matrix. So this plus 2 is a remain as it is. So this 1 times 36 minus 1, sorry, minus 3 times 0. Also this third term is also 0. So now the determinant here is 2 times 35 and it is 70. So now here the value of determinant of this matrix P is 70. So now let equate this multiplication of those four number is equal to 70. So now let's use this first property. The sum of those four number, it must be 15. So now let's sum the four number which are given in the option A. Here the sum is 15. So yes, option A may be the correct set of eigenvalues. Here the option B gives the sum as 10. So option B is not the correct set of eigenvalues, because it is not satisfying this first condition. Now option C, again it is not giving the sum as 15. So again option C is not the correct set of eigenvalues. Now again look at the option D. Here also the sum is 15. So I can say the option D may be the correct set of eigenvalues. So now we have cancel out these two options and we have to select the correct one from this A and D. So now let's use the second property. This one, multiplication of 4 eigenvalues, nothing but the determinant of this matrix P. Now let's multiply the 4 number which is given in the option A. So the determinant in this option A will be 0, and it is not correct because we are getting the determinant as 70. So now option A is also wrong. Now the only the remaining option is D, and it must be correct. Now also let's multiply those four number. Here the multiplication is 70. Yes, and yes, it is exactly same as the determinant. So option D contains the correct set of eigenvalues for this matrix P here. Now let's move to the next question. Okay, question 6 says consider a matrix M. Again we have matrix M, which is a dimension of 3 cross 3. One of the eigenvectors of M is, they're asking about the eigenvector. So the same concept about this eigenvector Ax equal to lambda x. Here this A is nothing but our any matrix. Here in this case matrix is M, and here this X is nothing but eigenvector. And here this lambda is a scalar and it's represent our eigenvalue, and again this x is the same eigenvector which is on the left hand side. So now let's go through these four options one by one. So let's start with the option A. So first of all, let's put this matrix here M as it is, because we need to multiply this X matrix with this vector A, and we are getting some vector, and we have to equate this vector into this lambda time initial one, and we are trying to find some scalar to represent the resultant vector after the multiplication. If we are getting any scalar, that's mean this vector is the eigenvector of this matrix M, and if we don't get any scalar here to represent the resultant vectors after the multiplication in this lambda time x, then we can say the vector given in the any option is not the correct one. So first of all, we need to multiply this matrix with the vector in the vector which is given in the different option. So let's put the vector here which is given in the option A. So now let's do the multiplication of those two matrices. So here the first entry here will be -2, and now the here the second entry will be -4, and the last one is again -2. So now let's try to find out some scalar here to represent the resultant vector here in this form lambda time x, and here the x is our initial matrix. In this case the initial matrix is this one, -1 1 -1. Here you can see we are not getting any scalar here for this lambda to represent this left hand side matrix in this right hand side form. So let's put not equal to here. In the other word, I can say the option A does not contain the correct eigenvector for this matrix M, because we cannot represent this matrix in this form lambda time initial one. So let's cancel out this option A. So now let's move to the option B. Now multiply this matrix with vector which is given in the option B, 1 1 1. Now again let's find the multiplication. So here this first entry will be 0. Also this again the second entry will be 0. In the same way the third entry is also 0. So now you can easily find scalar here to represent this 0 0 vector into this lambda time initial one. Simply if the scalar here take the value as 0, then we can say this left hand side and right hand side is going to be equal. So I can say here the scalar has particular value, here in this case 0. So now this vector 1 1 1 is satisfying this condition ax equal to lambda x or lambda equal to 0. So I can say yes, option B contains the correct eigenvector, because we can represent this resultant vector into this lambda time initial one, and here the scalar has particular value, in this case 0. So now in the other word I can say the determinant of this matrix M is also 0, because now we know the property relate the multiplication of eigenvalues, and the determinant multiplication of 3 eigenvalues is nothing but the determinant of this matrix M, and we know at least one of the eigenvalues of this matrix M is 0. So now I can equate this determinant equal to 0 for this matrix M. So now the determinant of this matrix M must be 0. Now let's also check whether we are getting the determinant as 0 or not. So let's find the determinant of this matrix M here. So simply 1 -1 0 1 -2 1 0 -1 1. So now here this word -1 plus 1 times, sorry, here again we are getting +1. So I can say -1 plus 1 and it is equal to 0. So yes, we are getting the determinant equal to 0. That's mean one of the eigenvalue is 0, and the same thing we are getting from this statement. So now we can say the option B contains the correct eigenvector for this matrix M. You can also check this equation ax equal to lambda x for the remaining option C and D. You are not getting any scalar to represent the resultant vector from this C and D in this lambda time initial one. So we can cancel out this C and D also, and the only option which is satisfying this ax equal to lambda x condition is given in the option B. So it must be a eigenvector for this matrix M. Okay, now let's solve question 7. For a matrix, we have a 2 cross 2 matrix. The eigenvectors are again the same concept that we used in our previous question number 6. The same concept ax equal to lambda x. Here, let's call this matrix as matrix A. So now, the same procedure that we did in the previous question, we have to do in this question also. So let's put this matrix here as it is. Let's again start with the option A. So option A has two vectors. There are some eigenvectors. So this matrix A is 2 cross 2. So it has two eigenvalue and correspondingly two eigenvectors. So every option contains the two vectors. So let's select this first one from this option A 1, 3. So now let's find the multiplication here. So here I am getting first entry as 16, and here in the second I can say 3 plus 9, so 12. So now if you try to find out some scalar here to represent this 16 comma 12 matrix to this lambda type initial one, so here you can easily say we are not getting any scalar to represent the left hand side matrix into the right hand side form. So let's put not equal to here. So now option A is not the correct set of eigenvalues because this 1 comma 3 vector is not satisfying this ax equal to lambda x condition. So now let's move to the option B. Again let's put the matrix A here as it is. Now let's select this first vector 1 comma 1. So now let's find the resultant vector. So here I can say first entry will be 6. Now here again the second entry is also 6. So now you can easily say here the value of scalar is nothing but 6. So here you can automatically represent this 6 comma 6 vector into this lambda time initial one. The initial one is here this 1 1 vector. So you can see this same vector on the multiplication side and on the right hand side. So I can say the eigenvalue here, let's call this lambda 1 is 6 for this matrix A, and one of the eigenvector is this 1 1 vector. So now let's try for this second vector which is minus 5 by 3 comma 1 to check whether this vector is satisfying this condition or not. If this vector is satisfying, then we can say the option B contains the correct set of eigenvectors for this matrix A. So now let's paste this matrix A here, and multiply this matrix with the vector minus 5 by 3 comma 1. Now let's find the resultant vector after the multiplication. So here we are getting minus 5 by 3 plus 5, and here I can say minus 5 plus 3. So now let's simplify it further. So I can say 15 minus 5, so plus 10 by 3, and here negative 2. So now the same process, let's try to find out some unknown scalar. Let's call lambda 2 such a way that we can represent this 10 by 3 comma minus 2 vector into this lambda time this initial one, and the initial one is negative 5 by 3 comma 1. So now you can equate this entry with this one. So you can easily say the value of lambda 2 here is nothing but negative 2, because if you multiply this lambda 2 with this vector, then this one will be lambda 2, and which must be equal to this negative 2. So one can say the value of lambda 2 here is negative 2, and yes, we are getting the value of scalar here which is negative 2. So we can say This vector is also satisfying this condition Ax equal to lambda x. So you can say option B contain the correct set of eigenvectors which are corresponding to this matrix A. Okay, now let's solve question 8. Question 8 says the eigenvalues of matrix A. Again, we have matrix A, which is 2 cross 2 matrix, are 5 and 10. So let's call it lambda 1. So lambda 1 is 5 and lambda 2 is 10. For a matrix B and B equal to A plus alpha I, where alpha is a constant and I is 2 cross 2 identity matrix, its eigenvalues are. So they are asking about the eigenvalues of this matrix B, and we have given the eigenvalues of this matrix A here, which are 5 and 10. So now simply here also we have to use the property of eigenvalues. If any matrix is formed with the help of this matrix A in some polynomial form, then the eigenvalue of the resultant matrix is nothing but just simply the same operation is performed on the eigenvalues of the initial matrix. So now simply we have to put this 5 here at the place of A here, and second time we have to put this 10 at the place of A to find two eigenvalues of this matrix B. Here this matrix B is also 2 cross 2, because here this matrix A and the identity matrix are 2 cross 2. So after addition of those two matrices, again we are getting the matrix of second order, and they're asking about the eigenvalues of those matrix B. So let's call its lambda B1, first eigenvalue for this matrix B. So now here let first replace this A with this plus 5 to find the first eigenvalue. So I can say here 5 plus alpha times. Now this identity matrix is replaced with 1, because all order of identity matrix are nothing but just simply its diagonal entries are 1. And if you find the characteristic equation, and then you will find the all the root of this any identity matrix, it's nothing but 1, and simply it's mean that all the eigenvalues of any identity matrix are simply 1. So let's replace this identity matrix with 1. So I can say the first eigenvalue for this matrix B is nothing but 5 plus alpha, and now the second eigenvalue, let's call it lambda B2. It is the second eigenvalue. So I can say 10 plus again alpha times 1. So I can say 10 plus alpha is the second eigenvalue for this matrix B. So now option C contains the correct set of eigenvalues which are corresponding to this matrix B. And here the eigenvalues are depend on this scalar here, this lambda, this alpha. If alpha is changed, then the eigenvalue is also changed. Okay, now let's solve question 9. Consider the system of equation. We have a linear system of equation which is represented into this matrix form X equal to B, and here this A is nothing but our coefficient matrix. Here the X is our variable vector. Here the variable are x1, x2 and x3, and this B is nothing but the right hand side of all equation in this vector form. So now they are asking about the value of this x3, this unknown, round out to the nearest integer. So simply to find the solution of this x3, we have to first of all form the augmented matrix from this matrix notation. So we need the augmented matrix. So now let's find it here. So simply we have to put the coefficient vector here on the left side. Let's put the vertical line here and put this vector B here. So now we have converted this X matrix notation into this augmented form. So now here you can see we have only 3 unknown, x1, x2 and x3, and we have 4 equation. This first equation, second equation, third equation and fourth equation. So now we can say this system of equation is overdetermined, because for solution of this 3 unknown we needs only 3 linearly independent equation, but here we have 4 equation So we can say if at least one equation is linearly dependent on other three, then we can say the system is consistent. So now here, what we have to do, just simply we have to reduce this augmented matrix into echelon form. For that, we have to perform some row operation. So now, to reduce this matrix into echelon form, I need this entry as 0, this also as 0, and this entry is also 0. So simply, let's subtract this first row, second time from this second row, and fourth time from this fourth row, and again 2 times from this fourth row. So I can say R2 minus 2 times R1, it will give me new R2. The same way R3 minus 4 times R1, and it's again give me new row 3, and row 4 minus 2 times row 1, and it's give me new row 4. So now after those 4 row operation, what we are getting, let's write it here, 1 3 2 1. So now this entry will be 0, and now here minus 6, we have plus 2, so I can say minus 4, and now here this entry will be again minus 4, and we have minus 3, so I can say minus 7. Now here negative 2 plus 1, so negative 1. Now in this third entry, here this entry will be 0. Now minus 12 plus 4, so I can say minus 8, and here this entry will multiply with negative 4, so negative 8, negative 6, it will negative 14, and now here negative 4 plus 2, so again negative 2. Now in the last row, here this entry again going to 0, here this will be minus 6, we have already plus 5, so I can say minus 1, and again this entry is minus 4, we have already plus 2, so I can say minus 2, and here minus 2 plus 1, so minus 1. So now what we have to do further, we have to reduce further this matrix into echelon form. So now look at this third row and this second row. If I multiply this second row with negative 2 and simply add in this third row, so the third row as all as 0, because it is nothing but twice as much this second row. So now let write it here. What we are going to do, we are subtracting 2 times second row from row 3, and it will bring us new row 3. So now after this row operation, what we are getting, this first row will remain as it is, this one minus 4 minus 7 minus 1, this third row all as 0, and this fourth is also remain as it is. So now you can see we have reduced this one row as in this 0 0 form, so we can say this third equation is linearly dependent on this remaining those three lines, then and then we can reduce any line in this 0 0 form. So now we have to further reduce this matrix to find this value of x3. So now let's perform one more row operation to get our answer of this x3 variable. So now again I want this entry as 0, because you can easily get after multiplying this fourth row with plus 4 and adding in this one. So I can say let's add negative 4 times fourth row in this second row, and it will give me new R2. So now if I perform this operation, then our resultant matrix look like this. Sorry, 1, this entry 0, again this 0, and this 2, negative 2 multiply with negative 4, so it will plus 8. We have already minus 7, so I can say we are getting plus 1, and here this negative 1 with multiply with negative 4, so plus 4, and adding in this negative 1, so I can say plus 3, and now here this third row remain as it is, and this last row is also remain as it is. So now we have reduced this matrix into echelon form. We can further write this matrix into this echelon form after interchanging some rows. So let's bring this last row and at this row 2. So I can say 0 minus 2 minus 1 minus 2 and minus 1, and let put this second row at this third place. I can say 0 0 1 3, and let's put this fourth row as 0 0. So now you can see we have reduced the matrix into the echelon form. All the entries below this entry are 0. Also all the entries below this negative 1 are 0, and all the entries below the this one are also 0. So now you can easily say the value of x3 here is nothing but 3 from this third equation, third row here. If you write the equation from this row, so simply you are getting 0 times x1 plus 0 times x2 plus x3 equal to 3. Here this 3 is represent the right hand side, so you can easily say x3 is nothing but 3. In the same way, you can also find the value of x2 from this second row and value of x1 from this first row, but they're asking about the only the value of x3, and which is 3. And now this type of process is called a back substitution, because we are going from the back. First we find the value of x3, and then we find x2, and then we find x1. So this kind of process is called as back substitution. So now let's move to the last question for this video. Now question 10 says consider the following system of linear equations. We have 4 equation and we have 2 unknown x1 and x2. Again we have more number of equation than unknown. Here the number of unknown is only 2 and we have 4 equation. So now again this system is overdetermined because we have excess amount of equation. Then we need to solve the system. To solve the system of 2 unknown, we need only 2 equation which are linearly independent. But here in this case we have 4 equation and only 2 unknown. Then if they are asking which one of the following condition ensure that the solution exists for the above systems. Okay, if they are asking about the necessary condition for this b1 b2 b3 and b4 which are on the right hand side in this linear equation, such a way that this system is consistent. If this system is consistent, then I can say at least 2 equation from those 4 equation, I can say at least 2 equations must be linearly depend on the other remaining linear equation. So now the same procedure here we have to use that we used in our question 9. Again let's form the augmented matrix also here. Augmented matrix. So simply put the coefficient here on the right hand side in this matrix, and let put this vector b1 b2 b3 and b4 here in this form. So now we have make the augmented matrix from this equation. So now further we have to reduce this matrix into echelon form to find the necessary condition for the solution. And the necessary condition for the solution of any system of equation is that if the rank of coefficient matrix is exactly same as rank of augmented matrix, then I can say the system is consistent. The necessary condition for the consistency of any system of linear equation is this condition. The rank of coefficient matrix must be same as the rank of augmented matrix. So now to find the rank of coefficient matrix and augmented matrix, we need to reduce this matrix into echelon form. So again to reduce this coefficient matrix into echelon form, we need all the entries below this one as 0. So this 2, this 3 and this 3, we want to make those 3 entries as 0. So now simply I can say if I subtract the 2 times the first row from this second row, then this entry will be 0 and it will give me new R2. In the same way, if I subtract third time first row from this third row, in the same way 3 times R1 and it will give me new row 4. So now after those 4 row operation what we are getting, so this first row will remain as it is here B1, and now this entry will be 0 and here this entry will be negative 4. Again here this entry will be 0 because we have already plus 4 and negative 4 come from this first row, and here this on the right hand side we have B2 minus 2 times B1, and now in this third row this entry will be 0 and here we are getting negative 6. We have already plus 7, so I can say plus 1, and here B3 minus 3 times B1, and now on the last row here 3 again we are getting minus 6 here. We have already plus 9, so I can say plus 3, and here B4 minus 3 times B1. So now we have to further reduce this entry as 0, this entry as 0, because you can easily reduce it by just multiplying this third row with negative 3 and add in this row. So it is easier to make this plus 3 as 0. So now let's perform one more row operation. Here I can write simply row 4 minus 3 times row 3 and it will give me new row 4. So now after this row operation our matrix look like this. Here B1 as it is, this second row is also as it is, B2 minus 2 times B1, and this third row is also as it is, and now here this row will be 0. I can say B4 minus 3 times B1, and I have to subtract this entry 3 times from this one, so I can say negative 3B3 3 times B3, and this negative 3 multiply with again negative 3, so I can say plus 9B1. So now it is our resultant matrix. So now you can see the here the rank of coefficient matrix, this one which is a 4 cross 2 matrix. Here the rank of this coefficient matrix, let's call its matrix A, here is 2, this matrix is A. And now if the system is consistent, they are asking about the consistency of the system. So now if the system is consistent, then the rank of this augmented matrix, this whole matrix with including this last column, it must also has rank 2. So now if this entry, now you can see here in the last column we have 4 entries. If those all 4 entries are non-zero, then the rank of augmented matrix will be 4, and if this is going to happen, then the system is inconsistent. So now to consistent this system, this column must have at least 2 values are 0 and which are corresponding to this one to make the rank of augmented matrix also 2. If this entry is 0, then you can see this second row whole as 0, and again if this third last entry is also 0, then this fourth row is also as 0. So you can say augmented matrix also has rank 2 because it has 2 non-zero values here. These two are non-zero. So now the necessary condition for this system has a solution. It is just simply we have to equate this first equation, this b2 minus 2 times b1 equal to 0. So I can say b2 equal to 2b1. This is the first necessary condition. That so now this is the first condition, that those this b1 b2 b4 sorry b3 and b4 variable must satisfy in order this system is consistent. And now the second condition is come from this last equation. So I can say b4 plus this negative 3 times b1 and plus this 9 times b1. So I can say plus 6 times b1 minus 3 times b3 equal to 0. So now it is the second condition, that this variable b1 b2 b3 and b4 must satisfy in order this system is consistent. So now look at the option. Option A give the correct this first condition, but now in the second condition they have given some other condition rather than this one. So option A is not the correct one because they have given here 3 times b1 and we are getting 6 times b1. So this condition not true. This one is true. So now let's move to the option B. Option B is not correct because they have given some other condition. In the same way option C is also wrong. Now look at the option D. Option D have given this first condition as it is as here, and also this second condition 6 times b1. So here 6 times b1 negative 3 times b3, so I can say negative 3 times b3 and plus b4, so plus b4 and equal to 0. So yes, we can say option D contains the correct condition for this b1 b2 b3 and b4 in such a way that system is consistent. Now the condition of this b1 here and this is not necessary because it can take any value. This b1 and this b3 minus 3b1 can take any value. Still I am getting the rank of augmented matrix is 2. It does not matter this b1 is take any non-zero or zero value. In the same way for this third entry also, so we are not getting any condition from those two entries. We are only getting the condition from those two entries here, this one and this one, because on the coefficient matrix we have reduced this row is 0 and this row is no as entry is 0. So we are getting the necessary condition from those entries only, from not those entries. So the necessary condition will come from this row and this row. So now we have solved the question and we have find out the relationship between those four variable in this equation form. And thanks for watching this video. See you later on the next video. Bye bye.